Hi, I'm Julien Froustey, and I'm going to talk today about neutrino evolution in the early universe. It was part of a work done in collaboration with Cyril Pitrou and Volpe. So what do I mean by early universe? In this talk, it's going to be the so-called mega-electron-volt age, which corresponds to the first second after the Big Bang, when the temperature of the universe was about 1 mega-electron-volt. And why is it such an interesting period? You have to keep in mind that at that moment in the universe, there are some neutrinos, antineutrinos, photons, electrons, and positrons. And they are all coupled through weak interactions between neutrinos and electrons and positrons, while in the electromagnetic plasma, QED interactions maintain equilibrium. However, as the temperature of the universe decreases, there comes a moment when the Hubble expansion rate becomes larger than the weak interaction rate, and then equilibrium cannot be maintained. Therefore, neutrinos decouple and form the cosmic neutrino background. And you can, when you put in the numbers, you can see that this happens about at a temperature of about 1 mega-electron-volt. And so we know from the study of relativistic decoupled species that below 1 mega-electron-volt, we expect the temperature of neutrinos to decrease as A-1 with A, the scale factor. If now we look at what happens in the electromagnetic plasma, we would expect basically the same thing. However, when there is this reaction of electron-positron annihilation and the reverse reaction, electron-positron pair creation, that takes place, but when the temperature goes below the electron mass, the reverse reaction cannot take place anymore, and therefore you will see a dramatic decrease in the number density of electrons and positrons that takes place at 0.5 mega-electron-volt. And it means that all the entropy that was contained in the electrons and positrons will be transferred to the photons. It cannot be transferred to the neutrinos since they have decoupled. Therefore, we expect, if we plot here the temperature times the scale factor, that for neutrinos which have decoupled, it just stays a straight line. But for photons, we see a sort of reheating due to this electron-positron annihilation. However, you can see that these two temperatures are very close, and that's why we expect some overlap between those two events. And this overlap means that we expect the final photon temperature to be a bit smaller and the final neutrino temperature to be a bit higher. We expect neutrinos to get some energy out of this process. Now, how can we describe it with some parameters? If we use the instantaneous decoupling approximation that is standard in textbooks, it means that we consider neutrinos decouple at a moment when electrons and positrons are still fully relativistic, and then electrons and positrons annihilate, but it's a separate event later in time. Then you can compute the ratio of the final temperatures, which is 11/4 power 1/3. And then you can write a simple formula with Fermi-Dirac and Bose-Einstein distributions, the energy density. However, from what I said before, we expect the actual energy density for neutrinos to be higher than this result. Therefore, it was parameterized with this parameter N effective, the effective number of neutrino species, that accounts for in terms of the photon energy density, this extra energy density, the fact that neutrinos have not decoupled instantaneously. And actually, you can put a whole bunch of physical phenomena that will end up changing the energy density, and you can account for them via this parameter. So we expect basically at least N effective to be higher than 3 in the standard case. So now we want a precise prediction for this number, because first it can be measured through experiments. I put here the latest experimental constraints, which are still at the order of 10 to the -1, and we would like a below 10 to the -3 precision for N effective, because at least we want to predict the number much more precisely than what is measured, and also we want to be able to use a very strongly constrained baseline to do some cosmological inference, for instance. Therefore, to do so, we need to think what are the physical ingredients we need to put in our calculation. First, the full decoupling process will be an out of equilibrium process. So we need to follow the distribution functions that I wrote here. And to do so, we need the Boltzmann equation with collisions. And to account for the whole energy transfer, we need also the full energy conservation equation. This has been done at the beginning of the century with many seminal works. But however, if we want to reach this precision, we need a few more things. First, there are some QED corrections in the equation of state of the plasma. That is because the formulae we are used to use consider free bosons, free fermions, but actually there is a bath of electrons, positrons, and so you have some extra contributions that you need to take into account, and that change NF at 10⁻³ level. And then the most complicated thing I would say is the fact that neutrinos are not massless, and so the fact that there will be mixings between the flavor states will make the Boltzmann description with just simple distribution functions not possible anymore. And that's what we will need to, that's what I'm going to present now. But just the previous reference calculation, and I will explain what our calculation, what are the upgrades in a way of our calculation, was done in 2016 and reached the 3.045 value that has been regularly cited since then. So just a very quick reminder about massive neutrinos. In the standard model, strictly speaking, there are 3 species of massless neutrinos, but we've known for some time that there is a difference between the mass states, because neutrinos, at least 2 of them are not massless, and the flavor states, and the matrix between them is the PMNS mixing matrix, and that gives rise, for instance, to neutrino oscillations, the standard case. So due to this mixing, we need to promote the set of distribution functions to a full matrix, a density matrix with off-diagonal components that will really account for this mixing. And the natural question is, what is the evolution equation for this object? And there were some works in the past, namely, I'd like to quote the Siegel and Raffelt paper, that allowed to derive the generalization of the Boltzmann equation. And this is called the quantum kinetic equation. And I write here the form that is useful for us in our case. So this is the evolution equation for the density matrix at a given momentum. It only depends on momentum and the amplitude of the momentum because of isotropy and homogeneity. So on the left-hand side, you have the typical Liouville term. And then on the right-hand side, you have different contributions. First, the vacuum term, responsible for oscillations in vacuum. Then a mean field term proportional to the energy and pressure density of electrons and positrons. It's different from the usual MSW term, which would be proportional to the number density of electrons, because here we assume a symmetry, and it's really constrained. There is a symmetry between electrons and positrons. And finally, the last term is the collision term. The collision term is the most complicated one, and it contains contributions from the different processes that can take place: scattering between neutrinos and electrons, scattering with positrons, annihilation processes, and self-interactions, scattering, annihilations between the different neutrino flavors. And actually, this last term was always approximated in the previous works, for instance, with damping lag approximation for the off-diagonal components. And this is one of the novelties of our work, is to put it like directly without approximation. A few more words about the assumptions. I'm not going to talk about the CP phase. Actually, under the assumptions of no asymmetry, for instance, it can completely be included, but I'm not going to talk about that now. And QED corrections, in the previous work in 2016, they were included up to the order E square, and we added the EQ contribution that is actually not negligible, and I will just comment on that in the end. A few numerical details before I present the results. As usual in this kind of work, we use a discretization in momentum to be able to have a finite number of quantities that we evolve. And so we have grid in momentum. And actually, due to the particular form of the scattering amplitude, we can reduce the collision integral to a two-dimensional integral, which gives for the full grid size n cube complexity term. And what we did also was to compute directly the Jacobian of the differential system, and this allowed us to really reduce the computation time. And I just want to mention that actually neutrino oscillations, there is a very, I think, elegant way to describe them, because actually you don't see, you will see in the results, you don't see actually oscillations. You only see them to be averaged throughout an adiabatic evolution. And so there is an effective way that really keeps the same accuracy in the results, but speeds up the code. And I refer to our paper if you're more interested, or to the discussion session. So the results. First, these are the results without flavor mixing, just to introduce the notation. This is the distribution function for a given neutrino flavor. And I will call T nu the effective temperature, because it's an out of equilibrium process. So there is no proper temperature, and it's just defined based on the energy density. And then on top of this effective Fermi-Dirac spectrum, we can define non-thermal distortions. And so what you can see is that electronic neutrinos, they have more higher distortions, they have higher effective temperatures, and this is due to the existence of charge current processes between electronic neutrinos and electrons and positrons. So this is the value of N effective we would get in this very well-known case. And now if we had the full quantum kinetic equation with the full machinery I described before, this is what we get. Very quickly, we see now a small difference between nu mu and nu tau. This is due to the differences in mixing angles. The different flavors get mixed, basically. And the new value of N effective we get is this one, and I will come back to the uncertainty on the last digit. But this is the new reference value, 3.044. So this slight increase between the no mixing and mixing case is due to the flavor conversion of electronic neutrinos. This frees some phase space for electron-positron annihilations to take place into electronic neutrinos. And this is the most favored channel because of the existence of charge current processes. Then I just want to highlight the large efforts that took place in the recent years. First, in 2019, the calculation of the E-cube contribution in the QED corrections that had been missed before, and actually changes N effective by 10 to the minus 3. It was confirmed the year after in the first calculation, including this term. And then we performed the first full calculation with the full collision term, also looking at the consequences in BBN. And this was confirmed by the joint effort by this team and the Salas team that had done the 2016 calculation with a very detailed study of errors, and our results are in perfect agreement. So it's really the community really came together to produce this result that is this new proposed value for N effective. And I also quoted the new value for the energy density today once neutrinos are massive. And so just one talk about the uncertainty. It's constrained at a few 10 to the minus 4, and this is due to the uncertainty on the mixing angles, basically, and the numerical uncertainty when we vary the parameters of the code. And finally, if we wanted to reach a higher precision, we would need to add QED corrections to the weak rates, and that would be a huge challenge. And then look at what would happen if we considered anisotropic cosmology, for instance. And this is also a huge and exciting work. And I thank you now, and I welcome any question. Thank you.